Now our formula for flux is the integral across the curve of f dotted with n with respect to the arc length, which we've come to do in terms of t by first off parameterizing our curve. So the curve that goes from 0, 0 to 1, 2 across the straight line could be parameterized like this. We'll take 0 plus 1 minus 0, which is 1, times t. So that would be just t. And 0 plus 2 minus 0, or 2t. So there's the parameterization for our curve, or the line segment, from 0, 0 to 1, 2. Now we will take that parameterization and using x equals t and y equals 2t, we will rewrite our vector field in terms of t. So x squared would be t squared, and y would be 2t. So there's our vector field in terms of t. Now we will calculate the normal vector, capital N, that we need. Now I did this in a separate video to show you why this works out the way it does. However, the calculation is simply to take the derivative of the y component, the derivative of the x component of the parameterization, and make that negative. So for our problem, y prime would be 2, x prime would be 1 with a negative on it. So there's our normal component. We need the dot product of those two. So that would be t squared times 2, or 2t squared, and 2t times negative 1, which is minus 2t. It's not a vector. So there's f dot n. So we need to compute the integral from 0 to 1 of 2t squared minus 2t. Now that's easy enough to do by hand. That's 2t cubed over 3 minus 2t squared over 2, which is just t squared, which is a 2/3 minus 1 minus 0, which comes out to be negative 1/3.